We're partnering with M3DI to demonstrate automated programming for structured light scanning workflows with the consumption of model-based definition parts via PolyWorks Inspector. This technology and software provides the ability for manufacturers to execute inspection programs, output completed reports, and upload those reports to your inspection directory. Let's show you how to get started.
Hi, I'm Nasir Mannan, Principal Engineer here at the Connecticut Center for Advanced Technology. Today, we're going to be talking about how we can leverage model-based definition to set up our inspection program automatically. We're going to be using two key technologies, a structural light scanner from M3DI called the VeriScan Auto to actually capture the data that we need off of our part. And then we're going to be looking at PolyWorks Inspector Software and how we can set up that software to consume MBD. We're going to be starting off in PolyWorks Metrology Suite Workspace Manager, and we're going to launch PolyWorks Inspector Software by clicking on the inspector icon. With the software open, we want to define a couple of things. PolyWorks supports two different inspection standards, the ISO and ASME. We want to make sure that we set up the correct standard before we import our model-based definition. So in PolyWorks, we're going to set up our standard by searching for the GD&T standard. And we're going to make sure that this is set up to ASME Y14.5. We're going to click Apply and OK. The next thing that we're going to do is set up our environment units to be in inches. So down at the bottom right, we're going to change from millimeters to inches. And now we're set up to import our MBD. If you click on File, Import CAD Models, we're going to select our native SOLIDWORKS part file and click on Open. We get a PMI import log, and we can take a look at all of the PMI that's on the CAD model, and more importantly, which PMI was imported and which one had errors coming in. In our particular case, all of the PMI was imported successfully, so we can close out of this dialog, and we can take a look at our 3D scene. And notice all of the PMI that's showing up on the CAD model. If we were to set this project up without model-based definition, we would have to go in and manually create all of these features and then assign the tolerances within which these features have to be produced. We'd be looking at a 2D print and just retyping in the information that we received from our customer into the inspection software. Here what we did was, by receiving model-based definition, all we had to do was a file import, and the entire inspection process is set up for us. This is saving us a lot of time up front. We can look at our feature tree and notice that under the feature node, we have all of our definition imported. So we have information about our planes, the cylinders that have to be measured, and then we have two slab measurements. In PolyWorks, the slab measurement in our particular case is the distance between two planes. So what we can do to hide all of the PMI is, if we click down on our middle mouse button, we can hide what's being shown in the 3D graphics area. And we'll take a look at our two slab measurements. So here we just have the CAD model visible, and we're going to take a look at slab 1. And what you can see here are the two planes that are highlighted, that are the planes from which the length measurement is being taken. In this case, we're looking for a measurement of 6 inches, and it needs to be within 10,000. If we take a look at our slab 2, notice that the other two planes on the left and the right side of the CAD model are highlighted, and this is indicating the measurement to be 6 inches within plus or minus 10,000. Now that we've imported our model-based definition, we just have to tell PolyWorks how to align our scan data set to our CAD model. With non-contact inspection, the scan data set will come in with the coordinate system of the scanner. Most often the case that the scan data set will come in not aligned to the CAD model. So in this case, we can just rely on PolyWorks functions to be able to align it. So the first thing that we're going to do is, knowing that on the scanning system that we're going to use, we're going to place the part the same way on our rotary plate every time, we can use what's called the pre-alignment. The pre-alignment assumes that the scan data set is coming in the same way every time. We're going to use a pre-alignment to get the scan data set close enough to the CAD model, and then we're going to use the best fit function within PolyWorks to do the rest of the work for us. So in PolyWorks, I'm going to import a scan data set that I had previously scanned. So I'm going to go to File, Import Polygon Models. I'm going to choose a scan data set. The object units are in inches. And you can see that on import, our scan data set is not aligned to our CAD model. Over in the feature tree, you can see for our data alignments node, we have only an original alignment right now. So we want to add in a manual alignment, which is going to be our pre-alignment. So prior to going into the function, we do have to select the data set that we're going to apply the manual alignment to. So we want to select our scan data set in the tree and then go to Align Manual Alignment. And from here, we can put in rotation, translation. In our case, we're going to apply these separately. So the first thing that we're going to do is apply a rotation. And along the Z, it looks like we need to rotate the scan data set by 90 degrees. And I'm getting that by visually looking at the model, looking at a particular feature and noticing that it is 90 degrees out of rotation. So I'm going to rotate about the Z, and I'm seeing the Z axis pointing upwards, which is giving me the axis to rotate about. And for my X axis, I'm going to want to rotate, it looks like about 45 degrees. For my Y axis, I might want to rotate by minus 45. If I hit apply, that looks good enough. And we can hit close. And notice that in the data alignment node on our in our tree view, I now have a rotation alignment set. The next thing I want to do is translate my scan data set. So I'm going to go back to making sure first that my scan data set is selected in the tree. I'm going to go to Align, Manual Alignment. And this time I'm not going to apply a rotation. We've already applied that. I'm just going to go for my 3D translation. And I'm going to, again, look at my coordinate system in the 3D graphics area. And I can see from here that I need to translate my scan data set in the X direction, in the positive X, and then in the negative Y direction, and also positive in the Z direction. So for my X, I'm going to go with, since I know that the distance between the two planes, the front and the back, the left and the right, are 6 inches. I can see that I'm probably about 2 inches in, so I'm going to do another 4 inches in the X. That's going to be a positive translation. In the Y, I'm going to go -3. And in the Z, I'm going to go a +1. Hit apply. And you can see that that brings the scan data set closer to the CAD model. I'm going to choose to actually apply another manual rotation to this to get it slightly closer. So if I, again, make sure that my scan data set is highlighted, I'm going to go to Align, Manual Alignment. And this time, I'm going to set my translations to 0. and I'm going to choose to rotate my scan data about the X direction in the negative 25 degrees. And that should be all I need. If I hit apply, that looks good. Close, and I'm going to apply one more translation. This time in the Z direction, I'm going to go -2. That looks good. Now that we have our pre-alignment set, the pre-alignment will get the scan data set close enough, and then the best fit alignment can then take over from there. At this point, we're going to set up the best fit alignment. To do that, we can go down to Align, and we can go to Best Fit Objects, or up here in our ribbon bar, we can go to the Alignments button, drop that down, and we have a Best Fit Data to Reference Objects icon. If we click on that, we can set up our parameters for the best fit alignment. In this case, we have as default pre-alignment checked on, and it's set to automatic. We can uncheck that since we already set up our manual alignment. We can leave everything else as default. Click Start. And you can see in the 3D graphics area that that best fit alignment now aligned my scan data set directly onto my CAD model. Click on Close. And now we can see in our tree view under our data alignments node that we have all of our alignments set from original to translation 2 being our pre-alignment, and finished off by our best fit alignment to reference 1. Now that we've set up all of our alignments and PolyWorks knows how to align our scan data set to our CAD model, all we have to do now is extract our measured values and then set up our inspection report template. To do that, we're going to go and right click on our features, and we're going to select Extract All Measured. And just with that single mouse click, PolyWorks has extracted all the measured values from our scan data set. If we go over to our Control Reviewer tab, you can see that we have updated all of the deviation values as well as whether or not that particular feature is pass or fail. You can see right away how this is an incredible time savings. On this particular part, I only have a handful of features that I'm inspecting, but imagine if I had 100 features or 200 features. Instead of going into the software, importing my CAD model, or if I didn't receive a CAD model, having to generate a CAD model off of the drawing, then importing it into my inspection software, clicking on each feature that needed to be inspected, fitting a feature to the CAD surface, and then assigning a tolerance. It's just saving me a ton of time. I'm not having to go through and click on each of those features. I can simply do a file import, and everything is there for me to use right away. All I have to do is set up my alignment. I can extract my measured values, set up my inspection report template, and I'm good to go. The more features I have to inspect, the more time savings you can actually realize out of this model-based process. So next, let's go back into our control reviewer, verify that all the measured values are good to go. And then what we're going to do is set up individual views that we're going to assign to pages in our inspection report template. Over here in the control reviewer, we can see that all of the measured values have come in except for cylinder 1 true position. We can take a look to see what happened there. If we click on it, right click, edit controls, you can see that we don't have assigned a diameter requirement. So if we click down, you can see that what's assigned is a slab. Instead, we want to change this to diameter. We can click out of it, and now that updates our deviation value as well as our pass or fail. This is typically as a result of not having received model-based definition in the best format. So if this was defined properly in the incoming model-based definition, I wouldn't have had to do that. But the inspection software here gives us the opportunity to actually correct for any missing values that are not imported with the model-based definition. Next, we can go into setting up our report template. In this case, we want to go back over to the tree view, and I'm going to hide my measured data set and just look at my CAD model. I also want to hide my coordinate system since I don't necessarily want that in my views. So I'm going to go over to my coordinate system node in my tree, and on the coordinate system world, I'm going to click down on the middle mouse button to hide it. If I click down on the middle mouse button again, I can actually see the coordinate system. So in different views, if you so choose, you can view the coordinate system or not. In all of our views that we're going to set up, we're not going to view the coordinate system. Next, I want to show the top projection of my view. So in the 3D graphics area at the bottom left where I have my coordinate system, if I hover my mouse over it, there's a cube that shows up, and it gives me an interactive way to assign what projection I want to look at in my 3D graphics area. So I'm going to click on the top view. And now I just want to be able to show the features for this particular view. So if I click on my middle mouse button for plane 1, you can see that plane 1 is assigned to the right side. We'll have a different view for that, so we're going to choose to turn that off. We'll look at our datum plane B. Again, that's on the left side. Datum plane C is our top surface here on the part. We do want to be able to see this in the top projection view in our inspection report. So what we're going to do is we're going to move the control. If we hover our mouse over it, there's an icon to position the annotation. We're going to click on that, and we're going to move the pointer to the center of the plane, and I'm going to actually move my annotation wherever I choose. I'm going to move it to the bottom right in this particular case, and then if you click on close, that'll place the annotation. If we view plane 6, plane 6 is showing a flatness call out. We do want to see that in our top projection. I'm going to hover my mouse over it and position my annotation. We'll look at plane 7. And position this annotation as well. Plane 8. And because I don't have space, I'm going to reposition my plane 7. Sorry, my datum plane C. Plane 9, we'll position this as well. And we're going to leave our cylinder views, our cylinder measurements for a different view, and our slab measurements for a different view. So in this particular case, we've set up our top view that we want to capture in our inspection report. To set up our inspection report template, we're going to make sure that in our 3D graphics area, we have everything the way that we want to view it. So I want to be able to zoom in on the part as large as I'd want the image to be captured in our report. We can go up into our report drop down in our menu, and if we click on create control view from 3D scene, what this will do is a few things. Notice in our tree view we don't have a report node yet since we haven't set up a report yet. So this will actually set up a report, and it will add the first page after the title page, and we'll be able to go over to our report editor and see that. So if we drop down our report in our menu, click on create control view from 3D scene, we're going to name this top view. And we have an option. If we drop down create report item, we can either just create the table the table will populate the information that we're seeing in the control in the 3D graphics area. We can create just a snapshot, so just see the a 2D projection of what we're seeing in the 3D scene now, or we can create both, create the snapshot and table. So in our case, we're going to create both. If you select on the button Create, notice now we have a report node in our tree, and we have report 1. If we go over to our report editor, you can actually see that we're on page 1. We have the 2D projection of the 3D scene, the way we had it set up in the graphics area. And then we also have our control view table here at the bottom. Moving back over to our 3D scene, let's now set up 2 other views. So we're going to hide our current controls that we have activated by clicking down on our middle mouse button. And let's set up our cylinder diameter views. So the first cylinder 1, we're going to view in the 3D graphics area. And in this case, I'm just going to set up my view to be somewhat isometric. And I'm going to want to now place my control. Same thing for cylinder 2. And for cylinder 3, 4, and 5. Now that we have that set up, we can go back to our report in the menu, drop that down, create control from 3D scene. We're going to call this our cylinder diameter view. And we're going to choose to create snapshot and table. Going over to our report editor, you can see in our report editor that we've captured that 3D scene, and we also added the table view. If we go back over to our 3D scene, we're going to hide our cylinder diameter controls. And for our last view, we're going to view our slab measurements, and we're going to choose to show slab 1. We'll capture a view for that. Report, create control view from 3D scene. We're going to name this as our distance 1 view. And we'll hide slab 1 and then activate slab 2. And we'll place this dimension, and we'll create a control view from 3D scene again for dimension 2. So distance view 2. If we go over to our report editor, you can see that we've now added in those 2 extra pages in the report, slab 1 and slab 2. For the title page of our report, we just want to add a 3D scene. We can do this by going over to the 3D scene, hiding any of the controls that we don't want to see, and we can position our CAD model in a view so we can see what that report is referring to. Back over to the report editor, we're going to click on Capture 3D Scene region, and I'm going to adjust my capture box. Using the right mouse button, I'm going to tune in my zoom. You can click on Capture. That will add my 3D scene capture to the title page of my report. Next, all we have to do is just add some other information, for example, the part number, the inspector name, the machine that the part was inspected on, by going into the properties of the report. In PolyWorks, you're going to find the properties next to the piece name up in the tree or above the tree. If you click on piece properties, we can add additional information. So in this case, our piece name is called mold. Our approval status is going to be, in this case, rejected. The date we can leave as default, the time we can leave as default. The serial number on this particular part we can add in. The order number. So this was on PO, and the operator name. We can choose to add an email address, and then we can also type in the name of the device that was used to measure this part. And then we can click on close. Now, if we wanted to export out the report, all we have to do is right-click on the report node in the tree and go over to choosing a type that we want to export to. So in this case, we're going to do a PDF file. And we'll just save it to our desktop for now as mold report 1. And click on save. This will then open up the report in a PDF viewer so that we can double check to see if the export was done successfully. That's it. With just a few mouse clicks, we've set up our entire inspection project. All we had to do was do a file import of a model-based definition file. All of the requirements for all the features that need to be inspected came in with that data set. In this way, we're saving a ton of time. I'm reusing information that my customer gave to me. I don't have to re-enter data manually from a 2D print. And I'm saving a lot of error that could occur from interpreting 2D drawings. All I'm responsible for is to set up my alignment based on the inspection system that I'm going to be using, and then my inspection report template. Once we've set up the report, we're ready to start scanning parts. To set up the automation, we're going to have to connect PolyWorks Inspector to the scanner software. So we're going to want to save out our project with a specific name, and then we're going to call that project in the scanner software to launch and then to transfer the scan data to run the inspection. In PolyWorks, we can click on this Edit Library button up here. This is part of our automation macro. So if we click on that button, it'll launch Excel. And in here, we're given the opportunity to set up our directory pointers and set up our inspection project name. So in our case, we're going to save our project as mold project, and we're going to set up our workspace path to be this path that you see here. Wherever you'd like to set it up, it's up to you. You just have to make sure that your part name, your inspection project name, and your path to the actual project is set up in this particular library. Once you have that set up, you can click on close. We save this project out as our mold project. Click on save. Once that's done, we can close out of PolyWorks Inspector. And in our workspace manager now, we can open up our mold project so that it's fresh without any scan data set in there. We can activate our start data file monitoring. And now we're ready to perform the scan. All we have to do is take our part and we can fixture it on the system here. Because it's a non-contact inspection system, the system will not put any force on the object. So I'm going to use a little bit of putty to hold my part down. I'm going to fixture it up off the table so that we can get underneath the part. In this case, all I have to do is make sure that my part orientation is the same every time. So I'm going to want my cavity to be facing towards the scanner every time I put a new part on. If you remember, we set up a pre-alignment, and that pre-alignment is assuming that I'm placing my part on the fixture the same way every time. Now that that part is down on the standoffs, all we have to do is go over and activate the robot. So on the teach pendant here, we're going to turn the motors on. We're going to reset the program to point to the beginning of the program. And then we're going to activate the robot. Now that the robot is activated, we can go over into the M3DI AO software. This is the 3D scanning, automation, and digital twin software. If we go over to our automation tab, we can first start the rotary system by toggling the offline button. And then we can connect to our robot. In this case, we're going to be a client to the robot, so we can click on connect. And we can execute our program. What the system is going to do is move the scanning device over to a particular vantage point so that the part can be scanned. The fringe pattern will be projected on the surface of the part, and the cameras will be taking images of that fringe pattern as it's being distorted on the surface curvature of the part. From that distortion of the fringe pattern, the system is able to calculate for that particular view that it's looking at the part from 3D points that represent the part surface. It does need to rotate the part and get different views because this is a line of sight technology. Any areas that are in shadow for the current view that the scanner is looking at on the part is not going to be captured. And so therefore the part is rotated and the robot is used to manipulate or move the scanner to different vantage points so that we can get the top, sides, and the bottom of the part. You can see that it happens very quickly. We're actually grabbing 45 million points per scan. And the system is on the screen here putting together all of the different views that are coming in. So all the views are pre-aligned. The rotary and the robot system are working together on the same platform. The system is pre-calibrated so that all of the scans come in their correct orientation. Once all the scans are in and we've captured enough views on the part to be able to then send it over to inspection to extract all the measured values, the system will take all the individual views and merge them together into a single mesh file. So the raw data set are points, but the software does polygonize this so that it becomes a mesh format, and we can export this mesh format out in several formats. In this case, it will export it out as an STL file. So you can see there that all the scans are captured. The system is now moving back into its home position. We have the completed program here on the screen, and it's prompting me that the program has been completed. At this point, the 3D mesh file is being exported out to PolyWorks so it can run through the inspection. Now that that scan is complete, we can simply put our next part on the scanner rotary plate. In this case, it would be Mold 2. We can go over to the scanner software since we already have PolyWorks set up and connected to our scanner software. We can simply click on Execute Automation. It'll run through the program, scan the part, export out the data to PolyWorks. PolyWorks will grab it, pull it into the inspection report template that we had set up, extract all the measured values, and output the inspection report to the inspection directory. By leveraging model-based definition, not only are we saving a ton of time, but we're also eliminating human-prone error by not having to interpret 2D drawings. We're using the data that's given to us directly by our customer, simply importing that in, setting up our alignment, our inspection report template, and we're ready to go. This is one in a series of videos that shows you how you can really leverage model-based definition to optimize your manufacturing programming processes. I'm Nasir Mannan. Thank you for watching.